in this lecture we will be discussing on atmospheric aerosols. We have so far covered air pollution, like gaseous air pollution and particulate air pollutions. This lecture is atmospheric aerosols. We will discuss that what is the difference between atmospheric aerosols and particulate matter. Okay. So, before we go ahead in this lecture, some of the slides in this lecture will be very common that we used in the previous lecture. So, in the first thing comes that what is the atmospheric aerosols. Okay. In the previous lectures we have already discussed that if we consider our atmosphere, Earth atmosphere, as a homogeneous mixture of gas, press, particulate, or we will come to that why it is called particulates. So, particles that is suspended in the air, then the whole system is called actually like here gas is actually like dispersion medium and particulate is a dispersed phase. Okay. Now, so if you consider these things, the second thing is that air here is actually like a kind of dispersion medium in which all the particulate things are suspended. If it is we are talking about the Earth's atmosphere, then it is generally called as atmospheric aerosols. So, this is very important. When we say aerosol, aerosol could be actually anywhere. For example, we use spray, body spray, it gives aerosols, right? That is also kind of aerosols. But when we stick to the things that are suspended in the air, and air is taken as a dispersion medium, and there are two things that can be there, either it is solid particles or liquid particles or both. Okay. So, this system is called as atmospheric aerosols. Okay. So, as I said, aerosols has been derived from two words, one is actually air plus sol. Air is here dispersion medium is simply the air. Now, here it is very important to understand that here when we say that air, the composition of the atmosphere remains the same throughout the discussion or wherever we discuss these things. However, the solid concentrations they can vary from places to places. For example, if you measure air composition, gaseous air composition, nitrogen, oxygen and argon, these are the three very prominent gases that are there. Then you have a series of trace gases. Ozone is there, CO2 is there, volatile organic compounds are there, methane is there, lots of things are there, they are there actually. So, these things, these trace gases can vary in concentrations, but the composition, general composition of the air remains the same. So, for example, oxygen is actually like for example, so if I just go next slide. So, if I say when we say oxygen is actually like 78%, sorry, it is nitrogen. Okay, nitrogen 78%, you have oxygen 21%, then you have argon which is about 0.9%. Okay, so this composition remains the same. This composition is not varying at all. Okay, but what is varying? The variation is actually mostly in the composition of the particulate matter. So, I said here sol means we usually when we say sol means solid, and when we say solid you can take the examples of any like dispersed phase here. There are so I have given some examples here like solid. When we say atmospheric aerosols, very broad. Fog droplets, now in the endogangetic plane specifically you will see lots of fog droplets are there. If you just drive your car or your bike, and if you are wearing on the top of that lots of fog droplets will be deposited, or fog droplets are deposited in the nights actually. So, because when the surrounding becomes cooler, they becomes try to condense on this one. So, in the daytime you do not see because the temperature is warmer. So, that they are actually in the kind of water vapor form, but when the temperature becomes cooler, the water vapor condenses and then they are deposited on the surface, earth surface. So, this is actually fog droplets that we call it, and we will see that how they are important in the later slides probably. Then you also have a bacteria and virus. We all have heard about COVID-19. In the air, if you measure, there are lots of bacteria virus, fungi, they are actually already present in the atmosphere. So, we will talk about that one, that comes in another category. Not only that, when we say aerosols, generally solid, as if you see in the slides, it's liquid particles can also be there. So, for example, rain droplets, snow or graupel or hails, they are also considered as a solid particle, liquid particles, which is actually the system when you have a rain droplets and air, atmospheric air, then it is called actually like that can also be called as atmospheric aerosols. So, be clear that when we say aerosols, it is not only the solid particles, it does include the liquid particles. Okay. Here the important thing is that how long we can go in sizes, and we will come to that one. Okay. So, as I said that when we say bacteria and viruses and fungi, these are generally classified as biological aerosols, and these are gaining a huge importance in the current situation, because these viruses and these bacteria, they are already present in the atmosphere, and because they can cause infectious diseases, they are and then they can disturb your respiratory system. So, they are actually considered as a very important one. Not on the other perspective of the bioaerosols, biological aerosols are also very good cloud condensation nuclei. We will come to that one later, but just to give you an idea that biological particles that can act are biological aerosols, they are actually very good cloud condensation nuclei. Okay. And this is, you can see the examples. So, if you see here, it is very important that the gas molecule size is like actually 100 ppm to 1 nanometer or so. This actually will be your gas. Then the next things comes protein, virus and bacteria, spores and pollens. These are general classification that you call it. And if you see the size between 1 nanometer to 1 micrometer, or if you see this one, and this red dots 1 nanometer to 100 micrometer, this is of our great interest, and this is actually we called it atmospheric aerosols. So, be clear here that when we say that atmospheric aerosols, we generally talk about atmospheric aerosols whose size varies from 1 nanometer to 100 micrometer. Now, if you see the classification here, and you can just remember that ultra fine, fine and coarse. Okay. We will come to that one, we also have a slide on this one. So, ultra fine means fine is in between. If the fine particle size is between somewhere between 100 nanometer to 1 micrometer, or 2.5 is also taken as fine particles, and less than that is actually called as ultra fine, and more than 2.5 micron particles, they are generally called as a coarse particle. So, you have a very different classification here within the aerosols. They are generally classified as ultra fine, fine and coarse particles. So, these becomes very important, and example of ultra fine particles will be sulfate particles, secondary organic aerosols and soot. The terms looks like very unfamiliar. We will come to that, what is actually secondary organic aerosols and soot, sulfates, how they are generated, we will discuss that one. And in the fine, just if you just go beyond fine, mineral, you have mineral dust and sea salt spray, they are actually in the coarser mode particles. Their typical size distribution is more than 2.5 micron or so. And if you just see 100 micron is cut off for the kind of aerosol. We generally do not consider atmospheric aerosols beyond 100 micrometer, but if you see, as I said, that atmospheric aerosols means liquid particles can also be there. So, if you see in the precipitation events, you can have rain, snow, graupel and hails, whose size could be actually say from 100 micrometer to 10 centimeter. These size can also be there. So, in principle, they are also called aerosols. They can be classified as an aerosols. And then you have actually cloud and fog. Cloud here means cloud droplet, actually not the cloud as a cloud system as a whole, because cloud system becomes a very big things. So, you have a cloud droplets there, and then fog droplets, they are also considered in the atmospheric aerosols. So, some of the examples are given here, like protein, how it looks like, very small size, 1 nanometer size, zoom size you can see. 50 nanometer soot particles are example is shown in the B, then you can see lots of 500 nanometer particles. Actually here you can see lots of things that, and then 1 micrometer like bacterial and kind of biological aerosols, and then 5 micron is like dust or sea salt particles. So these are very, very important for us. So this here two things that should come to your mind, that when we discuss aerosols, for example, when I say that size ranges from 1 nanometer to 100 micrometer. So you can see that 100 upon 100 into 10 to the power 3 is nanometer if I convert. So this will be this much nanometer and divided by 1 nanometer. So we are talking about the order of magnitude of 10 to the power 5. So the size of the aerosol, atmospheric aerosol, varies from 1 to 10 to the power 5. So this is a very huge range of size distribution of aerosols that we are considering. So factor of 5 is 10 to the power 5, order of magnitude of 5 which is varying. So that becomes very huge system here. Again, just to give, this is the from the previous lectures we have already discussed this one, but just to give an idea, when we say atmospheric particles, anything that is suspended in the air or gas medium, it is called as actually like atmospheric particles. Aerosols is now when we say atmospheric particles, in the atmospheric particles the only solid, tiny solid or liquid particles are considered. Air or gas medium is not considered as a system. If you talk about the system, so atmospheric aerosols, when we say, it consists of two systems, what is actually dispersion phase and other is actually dispersed phase. But when we say atmospheric particles, here dispersed phase is not considered, only we say that particles. Okay. When we say aerosols, then particles and then surrounding gas medium is also considered. I mean dispersion and dispersed phase both are considered here. And when we say what is particulate matter, so aerosol can be a very one small unit of particulate matter is called aerosols. Okay. So this is very important, don't confuse with these words. Aerosols and particulate matter are very different. Particulate matter is an ensemble of atmospheric particles. But in the general term, when we talk about the atmospheric aerosols, aerosols also consist of different types of atmospheric particles. So in a way, when you say aerosol, your surrounding medium or dispersion phase is very important, but when we say particulate matter, dispersion phase is not important, here it is not considered. So you can say that atmospheric particle, then aerosols, and then particulate matter. So atmospheric particulate matter is a big are ensembles of atmospheric particles that are already there in the atmosphere. So if you just don't consider the air as a gas, then it will be actually called particulate matter, but if you consider this is as then actually it is become. But this is also very important to note here, that when we discuss in the chemistry or something in discussion, we generally call chemical composition of atmospheric aerosols. Although now remember here what we have done, so when we say actually chemical composition of atmospheric aerosols, so this means when we say we have already filtered, two ways we do chemical analysis, we will come to that, filtered particulate matter, okay, from air, and we have collected this on the filters. Okay. So we have already filter on this one, and we do the chemical composition analysis of this one. So because already we have filtered from the system, so that's why one of the reason is that these are actually not called chemical composition of particulate matter, they are called chemical composition of atmospheric aerosols. Okay. Why? Because the aerosols has been filtered from the gas has been separated out, so from the system, and they have been collected. Okay. And then I discussed that air is a dispersion medium and sol is actually solid particles, are like this is a dispersed phase. They are also called aerocolloidal or aerodispersed phase system. Okay. And particles vary in size, chemical composition and shape, they are huge variations in this one. Size I had already discussed that 1 nanometer to 100 micrometers, and they are classified as actually fine and coarse when we typically discuss the chemical composition, because ultra fine particles the chemical composition is very different. The composition is very different, and generally we discuss when the particle size distribution, we generally consider these two. We will come to that sources and other things. This is very important slide, that what are the importance of atmospheric aerosol. If there was no atmospheric aerosols, we discussed in this later slides also that our sun is there, it is emitting about at 6000 Kelvin temperature. Okay, the temperature of the sun is, outer shell of the sun is 6000 Kelvin, and when it reaches all the way to the earth's temperature, the temperature is about 15 degrees centigrade, are actually like 288 Kelvin. This is the earth's temperature, earth's global average temperature. Okay, global average temperature of earth. So this is the temperature. Now imagine a situation, what is happening here from 6000 to 15 degrees centigrade. If you just consider in Kelvin, so if you just take it 300 Kelvin, there has been actually 101 by 20 times reduction. 20 times the temperature has itself reduced. Now suppose, and we know that sun rays are actually considered as electromagnetic radiations. These electromagnetic radiations, when they travel in the atmosphere, they interact with these atmospheric aerosols and gaseous molecules that are present. So all the way they are there, and then if you just recall my previous lectures, I have given the importance of different layers of the atmosphere, and then why these things are actually they are very important, and then we have discussed these things, right? That why oxygen is there, why we have only elements like sodium and other things in the ionosphere. They are mostly in the form of ions. Then you have a stratospheric ozone is present, why they are actually, okay. And then we have a kind of homogeneous atmosphere that is considered here. So if there was no particulate matter, so what is does actually, this actually is either this can whatever the radiation is coming, either it can scatter back radiation, or it can reflect, or it can go scatter the radiation back to the atmosphere, or it can absorb part of the atmosphere. This is very important. So if there was no aerosol, this means there should have in principle there will be no scattering or absorption. So the radiation that is reaching, it would have been much higher, and if the radiation that is reaching on the earth's surface would have been higher, the temperature of the earth's atmosphere would have not been very kind of conducive to live here. Then another important is chemistry of the atmospheric air that can actually enhance particulate matter. Okay. So when I say when we will discuss this one, particulate matter or atmospheric aerosol composition, they are actually in two. One is natural and is then anthropogenic aerosols, and then on the same way we define it's actually primary or secondary aerosols. So secondary aerosols are usually found by the chemical reactions on volatile organic compounds that are there in the atmosphere through the secondary processes, and they are actually very important. So this oxidation process happens in the atmosphere, that changes the composition of the atmosphere, and then they can not only change the composition, they can change size, morphology and absorption properties of the aerosols. So this becomes a very important topic here again. Cloud scavenging is a function of atmospheric aerosol composition. This is very important. If there was no atmospheric aerosol, what would have been there? No scattering or no radiation, no scattering or absorption. First, that is gone actually. But one very important prominent thing is there, that actually you need for the rain, you typically consider what is the raindrop size, actually 10 millimeter plus or little bit higher, or whatever order of magnitude you can take. So let's say 10 millimeter, and atmospheric water vapor size is about 20 nanometer. From this 20 nanometer, the particles has to grow from 20 nanometer to 100 millimeter or sorry 10 centimeter, and then when they grow this way, then it becomes very important how they grow. The water droplets cannot just grow on their surfaces. Of course, they will initially grow on the surface there can be condensation or coagulation, and then coalescence process can be there. But these, when they are there in the atmosphere, they becomes very important. Aerosol particles act as a seed particles, and they actually called as a cloud condensation nuclei. So this becomes very important. Okay, and some of them are actually like hydrophobic, and some are actually like hydrophilic in nature. So some of them will inhibit those cloud formations, and some of them will actually lead to enhancement in the cloud formation. Then I also gave the examples of why we have eyebrows here, right? Why we have hairs in our nose. This is actually the natures that has been created, actually that nature has created, are given as a safeguard, sort of safeguard. Of course, because this fine particles can still penetrate to our deeper in the nose, and then finally to the lungs and different parts of the body, but it still prevents lots of things actually from this one. And this becomes very important. From here also particles can be stuck here, so they are not directly going to your air. So this is also we discussed. I will just quickly go through this one. So because we know that atmospheric aerosols are very important for public health, and now this is the situation that High Court has already given lots of warning to the Delhi government, and then even in the UP also, and then other states as well, actually, that this air pollution is becoming a cocktail. It's a composition that is derived and has a very toxic composition, so that cannot be sustained. Okay, so this is very important here. Then I talk about the chemistry, that is also very important. And then one very important thing is that because these aerosol particles can absorb water or on their surfaces, they can grow. So in principle they can enhance the Mie scattering. Okay, we will discuss this one in coming slides. Unfortunately, I have to cover a little bit in a different way, so that it can be, you can have an intuitive feeling, and then we will discuss more about the concept in the later phases. So visibility is very important here, that visibility, if the aerosol becomes very important, then the visibility will be low. The aerosol concentration is high, the visibility will be low. If the concentration is low, then the visibility will be higher. And similarly about the cloud formation, I talked about that if aerosols were not there, cloud formation will not be happening there. And ocean fertilization, this is another very important thing. Ocean has a habitat of lots of microorganisms in there. Now where these microorganisms are getting the food from are the nutrients, we call it nutrients. So this is a global biogeochemical cycle. These aerosols actually can be either supplied from the river or from the water, that is rainfall that is happening there, and then the other one is actually dry deposition of atmospheric aerosols. So this dry deposition of atmospheric aerosols serves as a very good source for nutrient aerosols. And then cloud formation I have already discussed. So some of these things we have already discussed in this one. So we discussed about this one. Then I give an example of direct and indirect effect of aerosols. Direct effect means which we directly see by your eyes, or we can visualize that one. Indirect impact which we cannot see. So direct effect is actually like radiative forcing. So I said that particulate atmospheric aerosols, they interact with the incoming solar radiation. So thereby either they absorb the solar radiation or they scatter the radiation, and by doing so they changes the radiation that is reaching on the earth's surface. We will talk about the concept of radiative forcing later, and then they lead to the formation of haze formation. We already see that one, haze, right? Haze, you can see that if the particulate matter is very important, and this is the time, November, December, this is the time when the haze formation will be very high. And then when you have very high haze formation, high degree of haze formation, the visibility reduces significantly. And then when visibility reduces significantly, your trains, flights, or if you are driving, you have to be very careful with this one. Several times the train are cancelled, or the flights are cancelled in this one. And then in the indirect effect is usually taken into two ways. Indirect means when we are not able to see this one, and you can, but we can, through science we can understand these impacts, right. So this is one is actually like cloud albedo effects. Cloud albedo effects, what is there actually? So what is albedo? Albedo we discussed in the previous lectures, that albedo is intensity of the incoming solar radiation, that is actually like reflected back to the atmosphere, divided by the total radiation that is coming to the earth's surface. So intensity of the reflected and reflected radiation to the intensity of incoming radiation, solar radiation. So for example, if I take the earth's albedo is 0.3, okay, and this 0.3 radiation we discussed because has come because of the many components like aerosols, clouds, and then you have forest, ocean, then snow covered in so that actually these things have they contribute to the albedo, and but the earth albedo is generally considered at 0.3. So now what will happen if you increase the solar number of particles in this one, that is the radiation is coming, compared to the one where you have very less radiation, what will happen? This radiation, they will reflect back more radiation. What will happen, right? Each particle will try to reflect back. So when they reflect back, what will happen? They will lead to increase in albedo, because your reflected radiation is increased. So if you see the example, the equation albedo is IR upon I0, if you see the reflected radiation is increased, okay, and this is why this will lead to the cloud albedo. So it will lead to the increase in the cloud albedo. Now as a consequence, what will happen? If the cloud albedo is increased, what will happen? Consider a second scenario. You have same liquid water content, it is actually constant, okay, and if you increase number of droplets, what will happen? So liquid water content per number of particles, what will happen? Actually it will decrease, because this is constant and number of particles are increasing. So if the number of particles have increased, you have less number of what you call cloud condensation nuclei, you will have less CCN. So when you have less CCN, the cloud formation will not be there actually. So this will do two things. If you have this one, then there will be reduction in the droplet size. So CCN, the CCN will be less, and because the CCN will be less, and at the same time there will be the droplet size that is growing, because the same liquid water content you have, and number of particles have increased. So per particles the liquid water content will be less. So the size of the droplet will be small, there will be a reduction in the size. When there is a reduction in size, what will happen? Particles, if the size is small, okay, if the size is small, it will not allow to grow. If it is not growing, and if we need a threshold radiation, threshold size for the rainfall. So if the raindrop is not up to the size, say about 10 millimeter or so, it will not precipitate. So there will be a decrease in precipitation. So the precipitation will be decreased, or if the precipitation is not decreased, at least it will lead to a delay in the precipitation, because the number of particles, this droplet size has reduced. So the droplet size needs to reach to that level so that it can. So we discussed about the direct and indirect effect of the aerosols. We have already covered this precipitation formation in the previous lecture. So because of the lack of time, I am going to skip this one, but this is very important size, okay. So when we say size distribution of aerosol, there are two types of size distribution is important. Either you consider by number, and other one is actually by mass. So mass size distribution and number size distribution, they both are very important. Number size distribution, why number size distribution is important? Because when you are discussing about the properties related to the surface area or scattering, you need to know that how many particles are there actually of their particular size, and rather than the mass becomes less important in that case. But when we talk about the chemical composition, then it becomes very important, and whether the particle is actually acting as a CCN or not, then this becomes very important. So, if you see here, generally these particles are classified into 3. I have already discussed this one: ultra fine, and then you have fine, and then you have coarse, COARSE. Ultra fine is actually generally considered less than 2.5 micrometer, okay, and more than 2.5 micrometer is considered as coarse. So, you can see here ultra fine, and ultra fine is less than, say, about 100 nanometer. Okay. In this one, ultra fine, you have different kind of you have a nucleation mode and then accumulation mode. So, in the ultra fine, you have actually like nucleation, NaC, and then you have nucleation, accumulation, and then coarse. So, this is actually very important when we are talking about the number size distribution. If you compare to this one, you see the size distribution of number and mass, they are very different, isn't it? You can see very clearly bimodal distribution in the case of mass or volume size distribution. And if you see the size distribution where it peaks, PM 2.5 for the first peak is somewhere around 500 nanometer or so. Okay. And if you see just extend this one, it will go up to like say 2.5 micrometer. That is why it is first peak is called actually fine particles, which is actually PM 2.5. So, it starts all the way from say 100 nanometer or onwards to 2.5 micrometer. Less than 100 nanometer particles are generally called either nucleation mode particles. And then second peak, that is you can see here, is actually like speaking somewhere around 8 to 10 micrometer. So, based on this one, this is why in atmospheric sciences we considered only why we studied initially PM 2.0 and PM 10. There was no PM 1 actually. PM 1 very recently came because of their health impact studies, not because of the chemical composition. Of course, it is important, but initially if you see the look at the size distribution, if I say that if there was actually PM 1 here, then trimodal distribution, then actually it was there, but from beginning it was bimodal distribution, and the distribution of this bimodal distribution was peaking somewhere around 1 to 2.5 micrometer, other one was speaking 8 to 10 micrometer. So, they usually defined is actually PM 2.5 and PM 10. Then later we classified this one as PM 2.5 and PM 1. Okay. So, you have to be very important here. Now, there is another thing that you have to consider here. Nowadays PM 1 is actually called as a fine mode particles. So, now if somebody asks you that whether it is PM 2.5 is fine mode or PM 1 is fine mode, actually both are fine mode particles though. So, there is no very strict criteria here that whether PM 1, you can always argue that PM 2.5 is called fine mode, then what will be called as a PM 1? It is still called as a PM 1, is still called as a fine mode particles because of their properties that we have. And then PM 1, of course, PM 1 and PM 2.5, they are very important for not for the chemical composition of their 3 different PM 1, PM 2.5 and PM 10, they will be very different. Okay. And then they are, as well as their health effects. So, these are the things that you have to consider. So, I stop here for this lecture, and in this lecture we have covered almost like basic properties of atmospheric aerosols. In the next lecture we will discuss about the sources, how they are formed, what is actually their composition. Okay. Thank you so much.